Good afternoon, everyone. I'm Simon Huang from Wireless Communication and Applied Electromagnetic Lab. I'm here today to share with you about our research renamed continuously beam scanning phase arrays using low-cost phase shifting elements. The research is conducted under the guidance of Professor Matthew Chuang and Dr. Chu Hina. All right, so let's start with the outline first. I'm gonna divide my presentation into three parts. The first section, the introduction. I will describe the requirement for beamforming network in many commercial applications nowadays, and the key enable component for the continuously beam scanning phase array. Second, I've moved on to look at the design concept of the local phase control units and system schematic of multi-beam beamforming network. Continuous beam scanning array and its broadband realization. And at the end, I will draw some conclusion and about the research and put forward some idea about the future work. Now I'm going to start by introducing the motivation of the work. As we know, the principal objectives of next generation wireless communication are delivery of high data rate service for multi-user in variety of applications. The demand puts a high strain on the antenna system in terms of bandwidth, enhancement, coverage area extension, and power efficiency. Let's take a look at the picture here. The base station antenna need to cover a really wide spatial area where the user can be smart home, fixed wireless access point, macro cell, smart car, and so on. First, the operating bandwidth and the spatial coverage are always in demand. To address the problem with research, in this research, we design several beamforming networks which are capable of providing continuously wideband beam steering over a relative wide spatial coverage. So, in order to fulfill the design requirement, we developed the low-cost phase control units, which are used as a fundamental element. The units are originated from synthesized transmission line concept with the ability of changing characteristic properties based on the applied control signal. Some figures of the phase control units are shown in here. The upper figure is a PCB version, while the lower one represents the on-chip fabrication version of the phase control unit. In the next session, I will show you the working principle of low-cost phase control units, their properties, and the beamforming networks that is developed from this fundamental element. Firstly, let's take a look at the low-cost phase control unit. What we have in here is the two version of the unit cell, which on the left hand side is based on the pin diode and MEMS device structure, and it serves as a one on or off RF switch, while the other one is the design in form of the phase shifter with the ability of tuning its electrical length. Both of the devices are use low bias voltage and thus low power consumption. In addition, they also have comparable power handling capability. And as I have mentioned before, they are very much low-cost design. We are really suitable for many commercial applications nowadays. So let me introduce to you about the operating concept of the structure. The first is IF switch. The equivalent circuit of the structure is shown here, and the major part of this structure, the most important one, is about the CV in here, that it denote in CV in here. The router CV serves as the reconfigurable part of the structure. By applying proper voltage value, the resonance of this LC circuit is controlled. First, the structure operates at two different modes, on-stage mode and off-stage mode. At the on-stage mode, the design is equivalent to a transmission line, which has characteristic impedance Z0, and the electrical lamp is the combination of V1, Vs, and V2. Then at the offstage, the LC circuit is operating at the resonant mode, result in the infinite input impedance that we can see in here, Y in equal to 0. And as a result, no IF power can go through the circuit. And this what we call the offstage. And about the property of this design, we can list out in here is the low DC power consumption, the good RF handling capability, because the variable is characteristics, it can handling a very large power in RF. And also is the comparable on stage and off stage, on stage resistor and off stage capacitor, which represents the quality of the switch. And about the phase tuning element, the working principle of this structure, just the same like we have with the switch, that we have the capacitor value is controlled by the variable CV. However, after some manipulation, we derive that this synthesized transmission line can provide phase tuning capability without all its characteristic impedance. Our experience also point out that several stages of different electrical lamp can be achieved using this structure. The electrical lamp in here we denote as the 2 times Vs minus V2, and with different stage we would have the different electrical lamp. And the interesting thing in here is by changing the electrical length of the structure, the characteristic impedance still keep at the same level. And by this way, the other performance like the matching and also the isolation of the design will not change when we change the electrical lamp. And then it's leads to a design of 60 beam switching array based on 4 times 4 Butler matrix and this fundamental element. As we know that the array antenna beam direction is generated by the phase difference between the output port of the beamforming network. With a standard 4 times 4 Butler matrix, we only get 4 phase difference at the output port, and it is result in only 4 beam pattern can be achieved. But in this design, we try to increase the beam pattern of the uh, array antenna by cascading the phase tuning element. that we already learned about the working principle of the previous slide. And easy cascade with the standard pattern magic to create more output phase different scenario. So we can get more beam pattern at the antenna side. The fundamental beam pattern of the parametric we can see in here when we excited port 1, port 2, port 3, and port 4. And then when the parametric is calculated with the PS STL line, that's a type of synthesized transmission line that we developed, and is a 2-bit phase shifter. We can produce more output phase difference that we denote in here, and we separate it into 4 sets: set A, set B, set C, and set D. And in total, we can get 16 beam switching pattern. And that's how we achieve more beam switching pattern by using the PRSDL line and cascade with the standard 4-down pattern magic. So in the next session, I will show you the improvement of our beamforming network based on this initial design. In this session, we will try to answer the question that is very challenging. This is, can we turn the reconfigurable ability into tunable ability? Can we make the switching element become continuously tunable? And our research point out that the answer is yes. And in here, we have the on-off switch serve as a continuous tuning element. And the application we use in here is to train the phase tuning and power tuning of the of a coupler. And on the left hand, we have the equivalent circuit of the structure. And the right hand is the performance when we try to vary the variator's voltage. And then we got the different value of the capacitor tuning value. So we can see that's a phase and the power is changing when we try to vary the capacitor value. And this is performed in continuously tuning. And the next one is 1-bit phase shifter as tuning element. In this design, we try to implement a very flat relative phase shift when we change the frequency of the structure. And this structure is basically built by the left hand and right hand synthesized transmission line. And the relative phase shift of left hand and right hand synthesized transmission line is a kind of slope in here. And the two slope has the like the inverse direction. And when we combine these two structure, we can get a very flat relative phase shift. And about the reflection coefficient, we try to vary the capacitor in different stage to see the performance structure, and it seems like the performance structure is still good when we train the capacitor value. And this is what of the main property that I have mentioned before. Then when we try to train the electrical length of the syntax transmission line, the performance of the transmission line still keeps the same in terms of the characteristics impedance. And about the transmission coefficient, we got about the maximum of 2 dB loss when the frequency goes to the lower one or upper edge. And about the relative phase shift, we got a phase difference changing when we change the capacitor value. And the flash response we can see in here is very good at different frequency. This will in the future help us to realize the broadband beamforming network. And one of the application of the tuning element is used to enlarge the tuning range and the power like division range of the tuning power divider. The two issues existing on the tuning power divider is small tuning range of PDR, and also when we tuning the PDR, the phase of the output of the tuning power divider also change. This will cause a severe damage to your system. So by using the tuning element that I have mentioned before, we can create a tuning power divider with very wide range of PDR. And also, when we change the PDR the structure, only two output phase shift phase difference of the output port is generated, which is zero output phase shift or 100 minus 180 output phase shift. This is a improvement result when we compare to the literature that already published about the TPD. And the next one is the continuous beam scanning array. In this design, we try to create a one-time for power divider network that remove the SP40 needed. In communication design or the design of circuit about beamforming networks, the SP40 is a type of very lossy and the cost of the element is very large. So in this design, we try to implement the low cost design and remove the SP40 needed in the beamforming network structure. And the design have the two main parts. The first is tuning power divider, and the other is a type of modified 2x4 Butler magic, which is built based on fundamental structure like divider, phase shifter, and also 90-degree hybrid coupler. The core building block of this design is a TPD, tuning power divider, that we can provide a very wide range of power division ratio. And also, when we integrated all the structure into one, the transmission coefficient showing here show a very good result for the loss. And then, so also, is when we try to integrated that on the structure, we got the result that the overall gain of the arrays is around 8 dB at the maximum, and the minimum is around 5.8 dBi. And with the continuously beam scanning array, we firstly try to build the array that can scan in one dimension first, and then by stack up the one dimension beamforming network, we got the 2D beamforming network in here. So to further improve the continuously beam scanning array, we develop a broadband derivation of the structure. And the broadband structure is built based on the theory of subset that point out in the literature here. And for basically a vector sum of two signals from TPD is excited the parametric input port, and then we will got the output port phase progressive of the parametric to excite the antenna array. But with the parametric traditional parametric, we just got four beam direction. This is not good enough for now like a commercial application. So with this concept of subset, we can steer the beam direction of the array antenna into five subsection region, which means that with the excitation of two couple of input port of the parametric, we can got a subsection that the beam direction is still within this. And in total, we have five subsections represent for five combination of the two input port of the parametric. And the design concept is based on the equation that we show in here. After using the equation analysis, we can figure out that with the structure of Turing power divider, cascade with SPDT and parametric, we can fulfill the continuous beam scanning array and enhance the bandwidth of the structure. The one requirement for this whole structure is that the Turing power divider, the SPDT, and also parametric is designed in broadband operating frequency, and that is the important requirement. So with the TPD, the core enable element of the structure, we got the performance like this. The S11 represent for matching condition, and also the PDR can vary from -20, -30 to 30 dB, which is type of very wide range of PDR power division. And also, it's also worth to note that the output phase shift of the TPD only switch from two different stage, which is 0 dB phase difference or -180 phase shift difference. This also very important for the TPD in our structure. And for more detail about the power division ratio, we can see in the figure on the right corner that pursuit frequency, the power ratio can switching at a very flat pattern, which means that in the broadband operating is also keep the power division ratio at the same level. And this is the layout of the structure where we simulated the structure in HFIS. The reflection coefficient remain good when we see at the S, S parameter. And also a selected case we show in here is when the progressive phase shift of the output port becomes zero. The transmission coefficient and also the progressive phase shift is shown in the figure. And then the important part of the beamforming network, which is the beam variation, is shown here. We try to vary the progressive phase shift of the output port and see how the beamforming network can generate the beam pattern. And as we mentioned that from minus 30 to 30, we got a very good result in terms of the beam variation error, and also the side lobe level of the structure still remain very good. However, in the beam variation of 45 or minus 45, when it's moved near to the edge of the spatial coverage, we got the side lobe level a little bit large, and however, it still remain below the 10 dB of side lobe level. That's enough for the commercial application. However, in here, we still think that we can have some improvement in the design of the structure to improve the side lobe level and the pattern of the array antenna when we steering the beam to the edge of the spatial coverage. And in here, we show the spatial coverage of the array antenna, and this means that this is one of the very important property that we need to consider when we try to design the beamforming network for the next generation of the communication. And in the figure, we can see that the maximum coverage of the structure is about 120 degrees, and in the realization scenario, is can cover a very large spatial coverage. And about the conclusion, we have shown you the phase control units that originate from the synthesized transmission line. And with this phase control unit, we can either uh, build a on-off switching or delay line that can uh, s- that can fulfill the requirement to design the continuous beam scanning array. That's suitable for many applications in commercial because we have the property of low cost, low power consumption, and the design concept is easy to fulfill, easy to fabrication. And about the future work, as I have mentioned before, the beam pattern of the array still have some problem when we try to steer the beam at the edge of the spatial coverage. So in this scenario, we think that we can try to develop a concept to excitation the bathymetric input port about four or three input port at the same time, and then we will have more flexibility to control the beam variation at the edge of the spatial coverage. In this way, it will have the potential to improve improve the performance of the whole structure. And thank you for the attention.